Hi learners, welcome to the course Data Mining. We are into the third module and we have covered the classification and club prediction first part, and now we will cover the second part of it. The topics I will be covering today is the attribute decision tree induction. In that I will cover the attribute selection measures properties, tree pruning, scalability of decision tree induction. In the third part, we are going to discuss about the bias classification method and its examples. So let's get start. Attribute selection measure property. The first one is information gain. ID3 uses information gain as its attribute selection measure. If the node n represent a whole the tuple of partition D, the attribute with the highest information gain is chosen as the splitting attribute of the node n. If the attributes information gain, we have to measure. So which the attribute which will be the highest information gain will be the chosen for the splitting attribute. So this attribute minimizes the information needed to classify the tuple in the resulting partitions and reflects the latest randomness or impurity for these partitions. So here the information needed to classify the tuples in the resulting partition, and that reflects the least of the impurity, least of the randomness, which is not in the order to random, which is the least randomness. That is the term we call as a impurity for these partition. So such an approach that optimizes the expected number of tests needed to classify for the given tuple, and that guarantee that a simple but not necessarily the simplest tree is found. The expected information needed to classify a tuple in D. That is the formula for this is info of D is equal to minus summation of m to I is equal to 1 pi log 2 pi x. So that is the formula to classify the expected information to gain the information that is needed to classify the tuple, where pi is the non-zero probability that an arbitrary tuple in D that is belongs to the class Ci, and that is estimated by mod of Ci, D, mod of modulus D, and a log function to the base 2 is used because the information is encoded in the B. Its info D is also known as the entropy of the T. The second name of the info of D is also the entropy of T. So information needed after splitting using A into the V partitions. So the formula will be that for info of A of D is equal to summation of V to J of 1 modulus of Dj divided by modulus of D into info of Dj. So that is the formula that is needed to use after the split for the using A. Information gain is defined as the difference between the original information required. That first, the original information required, that is none other than the based on the just the proportion of classes, and the new required information that is obtained after the partitioning on the A. That is, the formula is gain of A is equal to info of D minus info of A of D. So for this we need to calculate the info of D first, info of D first, info of AD on the second, and then we will able to get the gain of A in minus of info of D and in minus of info of A of D. The highest attribute A with the highest information gain of A, is chosen as the splitting attribute at node n, the root node n. This is equivalent to saying that we want to partition on the attribute A. That would be the best classification. That would be the best classification. So that the amount of information is still required to the finish classifying the tuples in the minimum. That is in the minimum. So the second property is grain ratio. The C4.5, a successor of ID3 that uses an extension to information gain known as the gain ratio. So that we were using for the ID3, which, the measure was for that information gain, and for C4.5 the measure for that is the gain ratio that uses the extension of information gain, that is called as a gain ratio, which attempts to overcome this bias. It applies a kind of normalization to the information gain using a split information value. So defined analogously with the info of D, as the formula is split info of AD is equal to minus summation of V to J is equal to 1 mod of dj divided by mod of D into log of 2 in bracket mod of dj upon mod of D. So that is the formula to get the split info AD. This value represents the potential information generated by the splitting training data set D into the V of the partitions that corresponding to the V outcome on a test on attribute A. Note here, for the each outcome, it considers the number of tuples having the outcome with respect to the total number of tuples in the D. So it differs from the information gain because it is having the numbers. It is considering the number of tuples that is having as an outcome with respect to the total number of tuples in the D. So so the difference will be the difference we will get in the information gain, which measures the information with the respect to classification that is acquired based on the same partition. So the formula for to measure the gain ratio of A will be the gain of A divided by split info of A of D. So whether we are going to calculate the gain ratio of the A, we need to calculate the gain info A of D and gain of A. After that, we will be able to calculate the gain ratio of the A. Gini index. The Gini index that is used in the CART. There was the CART classifier. In that, the measure is called as a Gini index. Using the notation the previously described, the Gini index measures the impurity of the D. A data partition, the set of training tuple as Gini of D is equal to 1 minus summation of m to I is equal to 1 pi whole square. So this is the formula to compute the Gini of D, where the pi is the non-zero probability that an arbitrary tuple in D belongs to the class Ci, and that is estimated by mod Ci D divided by mod D over m of the classes. Here, the Gini index considered as a binary split for each of the attribute. While we are considering a binary split, we compute a weighted sum of the impurity of each resulting partition. If we are having example, for example, if a binary split on a partition D and into a D1 and D2, the Gini index of D given the partition will be the Gini of A of D is equal to mod d1 divided by mod d into Guinea of d1 plus mod of d2 divided by mod d into Guinea of d2. So by this formula we can calculate the Guinea of AD. For each attribute, each of the possible binary splits is considered. That is, for the discrete valued attribute, the subset that gives the minimum Guinea index for that attribute is selected as the splitting subset. Okay. Next, for continuous valued attributes, each of the possible split point must be considered. The strategy is similar to the described earlier for the information gain, where the midpoint between each of the pair of sorted adjacent value is taken as the possible split point. Possible split point, right? Then the reduction in impurity that would be the incurred by the binary split on a discrete, we can say continuous valued attribute A. The formula for to calculate that will be the delta Guinea of A is equal to Guinea of D minus Guinea of AD. Another method is tree pruning. What was the tree pruning in decision tree? Tree pruning. For the tree pruning, we have to remove the branches which are not according to our selection attribute. Here, some of the points we will see. When a decision tree is built, many of the branches will reflect anomalies in the training data due to the noise or outliers. Tree pruning methods address this problem of overfitting the data. When the anomalies and outliers will reflect as in the training data, that is the condition we call as a overfitting. That is the overfitting of data. So here we from this problem we will using the tree pruning method. So that type of method typically uses a statistical measure to remove the least reliable branches. Right? The pruned tree trained to be smaller and less complex and thus easier to comprehend. They are usually very fast and better at correctly classifying the independent test data, that is previously unseen tuples, than the unpruned tree. How does a tree pruning work? How it working? There are two common approaches to tree pruning. First is pre-pruning and second is post-pruning. In the pre-pruning approach, a tree is pruned, means it is removed. There is another term related to that, removed by the halting its construction earliest. Upon halting, the node become as a leaf, right? If we will halt the node at a certain level, it will not be constructed, it will be the only leaf, right? Leaf. The leaf may hold the most frequent class among the subset tuples or the probability distribution of those tuples, right? If the partitioning tuples at a node would result in a split that falls below a pre-specified threshold, then the further partitioning of the given subset is halted. After that, the subset will be halted. There are difficulties, however, in choosing an appropriate threshold. We will also get some of the difficulty while we are going to choose the right threshold. In the post-pruning, which removes subtree from a fully grown tree, a subset at a given node is pruned by the removing its branches and replacing it with a leaf. Then what we will do in this stage, while we are doing post-pruning, it will remove the branches as a leaf. The branches will be removed by leaf, That will be the replaced by leaf. The leaf is labeled with the most of the frequent class among the subtree being replaced. Right? So this is the example of a tree pruning. In this, there is a unpruned tree in the left hand side and the pruned tree in the right hand side. This is a pruned tree. This is a unpruned tree. We can check here the A1 node is at the most at the top, and after that yes and no are the classes, and there are many classes at the last level, class A, B, A, B, B. In the pruned tree, we don't have the much of the classes. We only having the A1 node, and after that it is dividing in the yes, and then it will be constructed at and on the S and the yes. So this will be work as a pruned tree after the pruning, pre-pruning and post-pruning. The cost complexity pruning algorithm used in the card is an example of the post-pruning approach. This approach considers the cost complexity of a tree to be a function of a number of leaves in the tree and the error rate of the tree, where the error rate is the percentage of the tuples misplaced by the misclassified by the tree. That is misclassified by the tree. That is the error rate. So it starts from the bottom of the tree. It will work from the bottom to right. It will work from the bottom. That is up. Bottom to up. That is a bottom to up approach. For each of the internal node n, it computes the most cost complexity of the subtree at the node n. The node n, and the cost complexity of the subtree of at the n if it were pruned, because it was replaced by the leaf node. So the two tables, the two values are being compared. If the pruning of the subtree at the node n would result in a smaller cost complexity, then the subtree is pruned. Otherwise, it will be kept. Either it will be removed if it is having the smaller cost complexity. Either it will not remove if the node is not having the smaller cost complexity. A pruning set of class labeled tuples is used to estimate the class complexity. This set is independent of the training set used in the used to build the unpruned tree and of any tests used by the accuracy estimation. That any test set used for the accuracy estimation. This algorithm generates a set of progressively pruned trees. In general, we can say the smallest decision tree. That generates a set of progressively pruned tree, that is also we called as the smallest decision tree. After the pruning, we will get the smallest decision tree that minimizes the cost complexity is preferred. So we are also working on the cost complexity, so that minimizes from the if we are going to use the tree pruning method. So in the G 4.5, that is uses a method called pessimistic pruning, which is the similar to the cost complexity method in that it also uses error rate estimate to make decisions regarding to the subset pruning. So for the cart, the C 4.5 method, that is using the pessimistic pruning of the branches, right? Scalability of the decision tree induction. What if D, the disk resident training set of class level tuples does not fit in the memory? In the other words, how scalable is decision tree induction? So we will work on the scalability of the decision tree. The efficiency of the existing decision tree algorithm, such as there are ID3, C4.5 and CART, has been well established for relatively smaller sets of data. Efficiently becomes an issue of the concern when these algorithms are applied to the mining of very real world databases. Then what the scalability comes in the picture. The pioneering decision tree algorithm that we have discussed so far have the restriction of the tuples should reside in the memory. That will reside in the memory. In the data mining applications, very large training sets of millions are common. Most of the often the training data will not fit in the memory, right? Because it is having the huge data. Therefore, decision tree construction becomes the inefficient due to the swapping of the training tuples in and out of the main and cache memory, right? Main and cache memory, RAM and ROM. So, the most scalable approaches capable of handling training data that are too large to fit in the memory are required, right? So, earliest strategies to save the spaces included discretizing continuous leveled value, that attributes, and the sampling data at each node. These techniques, however, still assume that the training set can fit in the memory. Is it exists? We will check. Several scalable decision tree induction methods have been introduced in the recent study. Rainforest, for example, adapts to the amount of main memory available and applies to any decision tree algorithm. Any decision tree induction algorithm. The method maintains an AVC set. AVC stands for the attribute, value, and class level for each of the attribute at each tree node describing the training tuples at the node, right? So the AVC set of an attribute A at node N gives class level counts for the each value of A for the tuple at N node, the root node. The set of all the AVC sets are at a node N is the AVC group of N, right? The size of an AVC set for attributes A is node N depends only on the number of distinct value of N, distinct value of A, and the number of classes in the set of tuples at N, at the node N, that is root. So typically this size should fit in the memory, right? Even for the real world examples, real world data. Rainforest also have the techniques, however, for handling these cases where the AVC group does not fit in the memory. The attribute, value, class level does not fit in the memory. Therefore, the method has high scalability for decision tree induction in very large data set. So the Rainforest is the best example for to remove the scalability of the that is going to be used for the larger data sets. This is the example in which we can see the AVC sets for a data set which is having the four tables, right? In the left hand side, we are having the boys, we are having the two columns A's and by computer, which is also having the label yes and no. And the either we are having the row that is youth, middle aged and senior, and the values for the respective classes. On the right hand side we are having the class income by computer, and the yes and no labels for the by computer, and in the record we are having the low, medium, high rows and the respective value. In the third table, in the left hand side, we are having the student column and the by computer column, that is having the yes and no classes, and in the record row, it is having the yes and no, right? In the right hand side, it is having the credit rating and by computer, and fair and excellent as a row. So this is the ABC set for the data set. For example, for decision tree construction and classification rules, construction decision tree for the following data set, that is having the columns age, income, student, credit rating, and by computer. So from this we have extracted the four of the tables in the earlier slides. So the records we are having the as a youth, middle age, senior in the age column. For the income we are having the high, medium, low. These are the three classes. For the student we are having the S and no. For the credit rating we are having the fair, excellent. These are the two classes. For the by computer, S and no. These are the two classes. So the solution to solve this table, here the target class is by computer and the values are S and no, that we have seen in the earlier table. So while we are using the ID3 algorithm, we are constructing the decision tree. We have to construct a decision tree for the same table. So for ID3 algorithm, we have to calculate information gain, attribute selection measure. Information gain for the ID3 algorithm, right? So here we will classify the table as we are having the class P and N, and the by computer as S and no, and this is having the value 9, 5, and the total will be the 14. We will get from the these earlier table. So we will calculate the info for D, that is the information gain for the D, that will be the I of 9, 5, right? I of 9, 5, that is P N, right? So that will be the formula will be the minus P by N log of 2, the P upon total, which is total, right? Minus the another for P upon N like this, right? So this is the formula to calculate the information gain of any node, right? So here we have taken the minus 9 upon total 14 log 2 and 9 upon 14 again minus 5 upon 14 log 2 into 5 upon 14. So that the calculation of the whole will be the 0.940. That is very, very near to 1, right? So for this table, that is having the age P and total I of P, and we will calculate for the same, that is having the records U, middle aged and senior, and P is having the column P and N is having some values and total is having some values. We have also to calculate the I of 2, 3. These are the two nodes. For this, if we will calculate the information gain for the same, we will get the 0.970. Information gain of 40. If we will calculate this for the same, we will get the 0 value. And for if we will calculate the I of 3, 2, we will get the 0.970. So here we will again get a next table in which we are having the age, P and total, and I of Pn, that is having the same values we have taken in the earlier slide. So again we will calculate the info of age D, right? This is the info of age D, right? So to calculate this, we are having the 5 upon 14 of I to 3. That is the formula. If you are going to calculate the info of age of D, we have to calculate the P of N into info gain of the earlier, info gain of the node. So here we will calculate the 5 upon 14 into 0.970, right, plus 5 upon 14. For this, I of 40 is 0 into 0 plus 5 upon 14 into I of 32 is equal to 9.970. So after the calculation, the value we will get is 0.963, 0.693, right? Then we have to calculate the gain of the same. At the last, we need to calculate of the gain of the total tree. So then we will calculate the gain of the age, right? Because we are working on this column. Gain of the age is equal to info of D minus info of age T. So we have already calculated the info of D in the earlier slide. Now we have calculated the info of age of T. So we will put the values in this formula, that is 0.94 minus 0.693. That the result we will get the 0.247, right? So similarly, gain of income is equal to, if we are calculating for the another column, we will have to calculate the gain of the income, that we will get the 0.029. If we will follow the same procedure for the each of the value, while we have to calculate the info of D, info of age of T, info of income of G. While we are going to calculate the gain of the student, we will get the value 0.151. When we will calculate the gain of the credit rating, we will get the 0.048. So these were the calculations we have got from the above example. So finally, the age has the highest information gain because it is having the 0.247. Rest of having the low values. These are having the smaller values than the 0.247. So it is the selected as the splitting attribute. So from the age, we have to split the other of the nodes as the it can be the income, either it can be the student, either it can be the credit rating. So for the splitting the nodes, we have to calculate the info gain, or we can say gain, for the sum of the node. In this example, node n is labeled with age and the branches are grown for each of the attribute value. The tuples are then participant accordingly. As in this example, we can in this figure we can check the age that is splitted into the youth, middle aged, and in the senior. This is the table for that. This is the table for the same. From this, we have extracted the same of the nodes. So after that, if we are having some of more classes, we have to classify from this table. We have to work on these of the three tables. So the tree after splitting branches is, if we have worked on the youth branch, then after that we have got the student, and for the each of the branches we are having the another node, credit rating as yes no as at the last nodes. That results in the last node. So that all the decision tree works as a bottom to up. So the tree, after tree pruning, after that we will do the tree pruning to remove the sum of the cost efficiency. So we will have the this graph that is having the age, youth, middle age, and senior. And in youth, it is having the student, that they are having the yes and no classes. In the middle aged, it is having the class S. In the senior node, it is having the credit rating node, and then it is splitted into to the fair, excellent as a yes and no. So to less the cost efficiency, we have to do the tree pruning method. We have to apply the tree pruning method. So finally, the classification rules we will get from this, that will have the if age is equal to youth, if age is equal to youth, and also the student is equal to yes, right? Then he will buy the computer. Then he is going to buy the computer for sure. So this was the prediction we have got from the decision tree. So if the age and is equal to middle aged, and then he is going to buy the computer, right? So there is only one rule for this. If the middle aged person is there, so surely he is going to buy the computer, right? So for the third decision tree, for the third node, it is having if age is equal to senior, and also he is having the credit rating as fair, then he will definitely going to buy the computer. So these were the three classification rules we will get from the this pruned decision tree. So that was all about the decision tree, right? So in the next topic, I'll discuss about the classifiers, naive classifiers. So till then, thank you for the watching.
Like, share and subscribe. Hit the bell icon for more updates.